Today we're going to discuss some of the factors that play into the development of a growth curve. So, biggest one, of course, is growth rate. Populations will grow at their biotic potential when the birth rate is greater than the death rates, and usually this means significantly greater than the death rate. So, in a logistical population growth curve, you'll see this in the middle of the curve when the slope is the steepest. Now, depending on the carrying capacity, this might last for a while or it might just be a temporary phase. And as a population comes into equilibrium, birth rate will eventually be equal to death rate. Now, it is possible to overshoot equilibrium, and if that happens, death rate will become greater than the birth rate. If it's a logistical population, this is just going to cause it to slip back below carrying capacity so the birth rate can rise again. If it's talking about an exponentially growing population, this can actually cause the death rate to go extremely high because the population is very limited and cause the entire thing to crash. And this is always driven by the limits placed on the environment. So in this diagram, we actually see logistical growth and some of the environmental resistances that can influence logistical growth for an aquatic population. Oxygen supply in the water, food supply, disease is really important, one of the biggest limiting factors and one of the most underestimated. Predators, of course, and the space that they occupy. All of these ensure that exponential growth rarely lasts long in environmental or in natural environments, and it tends to make ecologists very, very nervous when it does. And that's because the limiting factors will slow it down. And if the limiting factors aren't slowing it down, the population runs a risk of massively overshooting the carrying capacity, which is bad times. Eventually, the environmental resistances will slow down the growth rate until it hits zero, or you can see a stable equilibrium like we have here, where you can just see that the population of the logistically growing fish is just hovering up and below carrying capacity. So when it overshoots, it doesn't overshoot it by much. So when it corrects itself and there's a die-off in the population, it's not a big die-off either. That contrasts with boom and bust cycles. So booms occur when populations grow rapidly, most commonly in R-selected growth strategies, but also sometimes in K-selected while they grow at biotic potential. But the bust occurs when the population size becomes much greater than its carrying capacity, and this results in a dramatic decrease in population size. Oftentimes it's driven by disease. It can also be driven by a lack of resources. So you can compare the boom-bust cycle with the K-selected strategy, and it's very apparent what happens. The R-selected species grows very, very rapidly. It massively overshoots carrying capacity, and then there is a massive dying. These are the busts. The busts are driving the population all the way down so that it doesn't really, it's going to take some time for it to cover. Now with the R-selected species, it can actually go through multiple of these boom-bust cycles before K-selected species even reaches equilibrium. So why then do most species use K-selection? Well, the bust always comes with the risk of extinction or extirpation in the case of a local extinction. So when you go through a boom or when you overshoot K, you get three options in terms of populations. You can stabilize it over time, which is what the logistical growth does. There can be a bust, which causes a large decrease in the population, which is what the R-selected does, or there can be a total collapse. And if you hit the total collapse, the population in that local area is gone. So all populations can overshoot or undershoot carrying capacity. It's just a product of population growth. But the massive overshoot, followed by the massive die-off, carries that risk of extirpation. So just in terms of genetics, it's much easier to pass on your genes if there's a constant population. And in terms of natural selection, a less riskier strategy, one that's more likely to guarantee genes get passed on and allow for evolution of that strategy to survive more often, is the one that doesn't come with the risk of everybody dying off. Other factors we have to think about are the law of minimums. Law of minimum is simple. It's much like limiting reagents in chemistry. Whichever limiting factor is closest to being the bare minimum required is going to be the one that limits the population. Like, you might not have a lot of oxygen in the water, but if you have relatively even less food, the population of fish is going to be limited by the amount of food, not by the oxygen. If the food increases, then maybe oxygen takes over as the limiting factor. But it's going to be the one that has the lowest of all of the required factors. Or another way of thinking about it, the one that is the most hostile that is going to limit a population the most. And I say most hostile because there's also the law of tolerance. And the law of tolerance is interesting because there's a toleration limit for every factor. And I say most hostile because in terms of temperature, especially, high temperatures can be just as dangerous as low temperatures. So if you have a really, really high temperature, that could actually act as your limit on the population.